So today we are going to study the new topic, magnetic field of solenoid. Okay, of carrying current. It's sol now. It's not sol. It's solenoid. I'll make it clear. Okay. Here I remove the upper one. Okay. So today we are going to study magnetic field of solenoid carrying current. But before we start, you should know what is solenoid. Okay. Remember, solenoid is a tightly wound a solenoid is a tightly wound helical loop from an insulated copper wire such that its length is very large as compared to its diameter. A solenoid is tightly wound. Okay, a solenoid is tightly wound helical loop from an insulated wire such that its length is very large as compared to diameter. Means, let's draw it. I'll draw it. Okay. Sorry, my mistake. And if I use rubber, you simply correct it. Okay, so this is an hollow tube. Okay, made of an insulated material, cardboard, made of cardboard, and I use simple pen. So the solenoid is a tightly wound helical loop. Helical means this. Okay, now the wire is wound around this tube. A tightly wound helical loop from an insulated wire such that its length is very large as compared to its diameter. Okay. The magnetic field around a solenoid can be considered as sum of magnetic field due to large number of circular coils. Now you can see there are so many loops. Here we have the 4 loops, so there may be more loops, and they are insulated. Means even though they touch each other, there will be no sparking. Insulated means they are covered from. Okay, just like a coiling. It is so to find out the magnetic field due to this solenoid. It is this solenoid is identical with the magnetic field of a bar magnet. Okay, the magnetic field, this solenoid is identical with magnetic field of bar magnet, where you remember in bar magnet the magnetic line of forces. If I use other pen, the magnetic line forces always start from south and enter. See here also. Like this. We start from south and end at north. And how to do, and magnetic okay, this solenoid, okay, it's not a lone wire. When the end of this solenoid is connected through wires, and means the wire ends or the loop ends are connected, let's say through a cell or battery is resistance. Okay, then so it is comparable, it's like a biomagnet. Do you remember in Nolan in childhood how to make a magnet at home? You simply wound wires, insulated wire on nail and connected other end with battery, which you so it so it attracts start, it's like a magnet, so it's simple. Solenoid is that way. It's a okay. Now we are finding, so it's behaving like a bar magnet. The magnetic field within the solenoid is uniform and parallel to the axis of solenoid. As you can see it, these red lines are parallel to the axis of solenoid. If I'll draw an axis, so almost parallel. Okay. Now our aim is to find out magnetic field produced due to this carrying at different locations. Okay. Now we'll start our things. So how to start? By constructing. This is a general thing, so I'll start a new thing. Cancel. I have to rub it again so that I can make. Okay, I'm just rubbing my whiteboard. It's a good tool, but as I'm using mobile, so text. So I'll at the top, I'll keep the topic. Now I use again to understand the working of. So at the corner, okay, just remember what I'm trying to do. Okay, now this is our solenoid, and I use simple that our circle part. Okay, if you want clarity, I rub it. Okay, now okay, and then I draw an axis. Draw the axis of this solenoid. We start from center over here. Let's say the axis names. This is an XY axis. Let's suppose an XY solenoid of radius R. The radius of this solenoid is capital R, remember. Or we can write over here. Okay, here I'll write 1 minute. Okay, so this okay, the radius of this solenoid is R. So I use different point to show that. Capital R is the radius of the solenoid. Now we have to find magnetic field, and let us say I current is in this solenoid. I am not drawing the wires which are wound over it. So let us say the current flowing in the conductor in this solenoid is I. Okay. Now to consider a given, now we consider this solenoid is, now to find out the magnetic field, we consider that solenoid consists of large number of small segments. So let us consider a segment of it. I use a straight line, simple it. Okay, this is an segment. Okay, part of it, this solenoid. Let's name it AB. Okay, let's name it an AB segment, because is a lot of, in this AB segment so many turns may be there, and its length is DL. Let's name it, I agree with what I'll do in the bottom, and the length is, this segment is DL. As we always do, we take a part of it. And this segment, okay, this segment is P x distance apart. Let's say here is your observation point. Let's say let me draw. Here is your observation point P. From this segment is, I'm just drawing it, remember, is x distance. I'm just remember. Okay, I'm drawing. Okay, just wait. So from here to here, complete. Okay, I'm just making it. This is x and this is DL. The segment length is DL, and this is point P. So this segment AB is x distance apart. Now the segment AB is, okay, let me, okay, where the segment field has to, okay, and P is the point where we are supposed to measure the magnetic field strength. Let's say that in this segment, AB, let's say the number of turns per unit length, I'm just writing, remember, number of turns per unit length is small n. Okay, per unit length. So in DL, so in segment AB, so in segment AB, so in segment AB, how many turns will be there? So we will simply get it by multiplying the length with number of turns. So number of turns is equal to n into DL. Okay, So total, so we have already defined in the beginning the number of turns per unit length is n. So the number of turns in segment AB is NDL. In AB is NDL. Okay. And let's say I'm defining, and let's from at the edge of this segment AB I draw a line. I use a straight line AP and PB as well. Okay, why I'm using it, you will understand. And let's say that, and because this AB is very small segment of this, what, okay, so we can simply say, so we are saying that AP is equal to BP is equal to R. Okay, AP and BP are R. I cannot write on the figure because it's a very small diagram. So because of this segment AB, the intensity of magnetic field at point P according to Biot-Savart law, or this segment, just it is just like remember yesterday we have studied the magnetic field on axis of circular coil. So it is, this segment is like a circular coil and P is on the axis of it. So the result we can do by using same, so final result we can simply say it, the magnetic field at point B, at point P due to this segment is simply mu 0 upon 4 pi 2 pi and I'm writing NDL is total number of turns. Okay, I R square upon R square plus X square 3 by 2. This is a, yes, last derivation we have done. So the magnetic field due to this smaller segment, but our aim is to find out the magnetic field at point P due to the complete solenoid, due to the, not because of this segment of this solid AB segment of solenoid, but, and to get it, again you know it, what to do, we are supposed to integrate. But before we integrate, we simplify our problems by changing variables, by using variable change of variable method. So let's do it. Use a method, the same equation we have used, we have derived yesterday. Okay, I'll just rub it, very small whiteboard. I'll try to, the market is open, so I'll try to buy and what we say, bigger screen resolution. Okay, now this is all we have now. Now how to change the variables, for that we again we have to modify it, the diagrams. let's to cover it. Okay, the change of variables. Okay, so now what I'll do, now I will simply use a pen. Let's say the PB make an angle theta. Remember, I'll use a different pen, otherwise you will be confused. Again, it is a different color, I should use it. So this angle, okay, this angle is theta. This angle is theta, and the AP, PB made angle with axis is theta, and AP make angle with theta plus d theta. Okay, so I am just writing here, remember. So it is BPY is equal to theta, and APY is equal to theta plus d theta. Okay, BPY, this is theta, okay, and APY is theta plus d theta. Okay, now after, and as we already said, AP and PB are at equal distance. AP is also R and PB is also R. Okay, just keep it in mind. And this is your radius of the solenoid. So as this angle is theta, okay, I'm just trying to theta. So from vertically so this angle would, this angle, so this angle also be PBA. So angle PBA also be theta. Why theta? It means that alternative interior angles. Okay. Open just now. Okay. Use pens, pencil to rub it because so much less space. There is no option of bigger. Now from the diagram, which triangle? From the right angle triangle ACB. ACB. Where is ACB? I have not mentioned any C point. Where is ACB? Okay. So what I'll draw from AP, I draw a perpendicular line. Remember what I am saying, from AP, from line AP. Okay, I am putting and perpendicular, drawing a perpendicular line on PP from point A. So this is a perpendicular line, so I draw it with pencil. It should be looking perpendicular. Yeah. So this where it touches is C point. So this point is C. So in this triangle ACB, in this right angle triangle, okay, right angle triangle ACB, ACB, this right angle triangle ACB, we're trying to find sine theta. So sine theta, from this AB we know theta, angle B is theta. So sine theta will be perpendicular upon hypotenuse. So it's simply AC upon hypotenuse, and hypotenuse means AB. And AB is, we know it, how much AB is DL. So I'll simply put a value of DL over. Instead of AB, I'll put DL. Or in simply cross multiplying, we got AC is equal to DL sine theta. Okay. Now angle D theta. Now from the definition, okay, this is clear. So AC is DL sine theta. Can Now where is your angle theta? This is angle theta. Remember, I am just putting an arrow. This is angle D theta. Theta plus D theta. So this one is angle. So from angle definition, D theta, why I am doing, you will understand. D theta, angle is, from angle definition, theta is arc upon radius. So arc it is AC and radius, and that is R. AP is R. So you will get again AC is equal to R D theta. Okay, so now we have two values of AC. First, but from earlier equation we got it is AC is DL sine theta is equal to R D theta. So wherever DL sine theta is there, we can simply put, or further we simply put, hold on for a second, I am coming. So now we are going through that part. So now we are putting DL sine theta. Okay, now I'll substitute the value over here. So we got from that, I can simply get DL is equal to R D theta upon sine theta. Okay, this is, remember this equation. Okay, this also I am removing because of the space. Otherwise every time I have to go for the new slide. I need a diagram because okay, now this is again one more thing we can find out for triangle PB from this triangle. Remember this right angle triangle, or simply say from this right angle triangle, the red one, I just broke it because it's right angle triangle. So we simply use Pythagoras theorem. So we can simply get I just first remove R square is equal to X square plus R square. Okay, so I'm going to put all the values back to the main equation from B. So dB was, okay, this all values I am going to substitute. So now first I'll write the earlier equation. dB is equal to mu 0 upon 4 pi 2 pi Ni 2 pi NdL, no? And dl I r square upon r square plus x square power 3 by 2. So in this first equation I substitute those values. So after substituting mu 0 4 pi 2 pi, okay, as it is, ideal, okay, dl value we already have calculated, so we are putting the value of, so dl is r d theta upon sin theta, and ir is square as it is, okay. But denominator, if you look at r square plus s square, which is small, it is r square, and I simply do r cube because it's 3 by 2, so it's simply r, okay, it is r power 3. So now we have, so this is transformation from dl to d theta, that's a change of variables. So one further, if I'll do that, I need a space. For that I need to rub the old equations. I think I'm keeping this what equations, so this diagram, because I needed to explain few more things from the diagram itself. Okay, so the final equations will be, after cancelling all the repeating terms, two pi and I, okay, after cancellation 1 r cancel from up, so r square sin theta, and here is your d theta. Again from the diagram, sin theta is r upon r, okay, from this diagram, this triangle, again I am taking, again I am measuring sin is capital R upon r, or r can be written as r sin theta, okay. I substitute these values in above equations. So the equation, simply after putting the value, after cancellation all the terms, okay, I am directly doing it. You can simply do it by your 0 upon 4 pi 2 pi Ni sin theta, and it is d theta, okay. The denominator will cancel itself. When I put sin theta is capital R upon small r, the denominator will cancel automatically. You do it by your own. Now this is magnetic field due to that segment, okay, dB. Now to find out the magnetic field due to complete solenoid which extends from x to y, So there we have to choose extreme point. For that, what I'll do, I draw a line from this point P to extreme end this M. Okay, I'll use different pen, otherwise reflect. Okay, and from this to other extreme point from P only. One extreme point and another extreme point from here to N is extreme point. M and N. I name it. This extreme point is M, and this one is N. Okay. Only thing I have to integrate this one. So I simply integrate from M to N. And we know from M, let's say the M angle from M, extreme end. So this whole angle, I'm drawing it. This complete angle is theta 1. And this complete angle is, okay, this one is theta 1 and this one is theta 2. I name it because here the value of theta varies from extreme M to N. So instead of M or N, I simply put N is theta 1 and M2 is theta 2. So simply we have to integrate it. So simply we have to integrate it. So after simply integrating, I'll take out all the component u0 upon 4 pi 2 pi n I. And as we know, only the term which was sine theta d theta. Sine theta is minus cos theta. Integration of sine theta is minus cos theta. And theta value ranges from theta 1 to theta 2. We substitute the value, we simply get the result. So on final, so the value of beta will be so on simplification 1 upon 2 mu 0 cancelling ni, okay, cos theta 1 minus cos theta 2, the complete case for solving it. Now special case in this, if point P lies at the end of solenoid, means point P shifted from here to here. Okay, point P shifted from here, point P. I use different pen. So point P extreme end, any one of the extreme end. In that case, theta 1 be 0 and theta 2 will be 90 degree. We substitute the value, to cos 0 is, to cos theta cos 0 is 1, cos 90 is 0. So our answer will simply come half nu 0 and I. Okay. One last case which is important. If the length of solenoid is greater than its radius, in that case remember theta 1 is 0 and theta 1 become 180. So theta 0. So in that way, if we substitute the value of this, the term which is in between cos theta 1 cos theta 2, this one cos 0 1 and mine cos theta 2, which is cos 1, it is minus of minus 1. Okay, so this become 2 and this 2 will cancel with denominator. So the solution will be simply nu 0 and I. So finally we got the result. So finally we got beta is equal to b is equal to nu 0 and I. When we have a long solenoid, infinite long solenoid, the magnetic field produced is nu 0, where is nu 0 is permeability, free space, and is number of turns per unit length, and I is current flowing it. And extreme, okay, this is and second value, which first value which we got is nu 0 and I upon 2 extreme end. Now you can see the value of how much difference, just a half of the beginning. So in a solenoid, anywhere it is nu 0. If the solenoid is lengthy, then it is nu 0 and I, and or you can say at the center. So at center the magnetic field strength is nu 0 and I, and at extreme nu 0 and I upon 2. So let's go